The new images obtained from the James Webb Space Telescope have astonished scientists, revealing an unexpected reality about the universe. Instead of simply expanding our view of the cosmos, these images have exposed a disturbing truth. Our ongoing understanding is insufficient to comprehend the possibilities of the universe in its infancy. The current theories regarding the universe's origins seem to be reaching their limits, which compels us to reconsider new hypotheses about its early stages. This raises the critical question of how the universe was shaped and why these discoveries are challenging even the most experienced space experts. As a result, there's a need to investigate the true nature of the Big Bang and its continuously evolving details. It may be time to reassess the Big Bang theory itself, as popular belief has often misrepresented it. The Big Bang wasn't merely an explosion within pre-existing space but was the very origin of space itself, unfolding about 13.8 billion years ago, alongside matter and time. One of the key features in real science and cosmology is the concept of a singularity, a point where gravity becomes so intense that the curvature of spacetime becomes infinite. After billions of years since the universe's creation, we now observe that our cosmic home exists as part of a vast collaboration. For scientists, this represents a crucial element of the universe's existence, emphasizing its ongoing expansion. The universe doesn't simply wander into pre-existing space. Rather, space itself continues to expand, as supported by traditional theories. The first stars are believed to have started shining approximately 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Age of the universe. This was the era when the first brilliant celestial objects gathered to form mature galaxies. However, the pace at which these galaxies developed remains a mystery. A significant breakthrough came in July 2022, with the James Webb Space Telescope's first images, which revealed various galaxies, some of which had already existed around 300 million years after the universe's birth. Despite being much younger than the galaxies we observe today, these early systems were considerably smaller and less massive, aligning with the scientific model of the time. In the early universe, the density of matter was insufficient to create galaxies as large as those we observe in the present day. The discovery began with 6 extraordinary redshifted bright spots detected by the James Webb Telescope, triggering one of the most significant cosmic mysteries of recent times. These newly discovered galaxies, although similar in age to previously recorded galaxies, appeared nearly as large as our Milky Way. This finding has sparked intrigue within the field of Big Bang cosmology. Upon analyzing a series of images taken with the telescope's near-infrared camera, scientists confirmed the presence of these distant objects, using redshift data to conclude that the light from these galaxies had traveled for over 1 billion years before reaching Earth. Consequently, these galaxies had already existed between 570 and 700 million years after the confirmed Big Bang event. This astonishing discovery challenges traditional cosmological assumptions, which predicted the formation of much smaller, less developed galaxies at this stage in the universe's history. Instead, the James Webb Telescope revealed galaxies nearly as large as the Milky Way, defying expectations. The gravitationally bound stars in these galaxies had already accumulated mass exceeding 10 billion times that of the Sun. One of these galaxies even showed signs of having a mass exceeding 10 billion solar masses. However, whether this hypothesis is entirely accurate remains unresolved. Even in this scenario, the mass present in the early universe would be much greater than expected, creating an even deeper puzzle. The discovered galaxies challenge nearly all traditional cosmological theories. Even if, by some chance, one of these galaxies is confirmed to be accurate, it would force us to reconsider our previous assumptions regarding the existence of these early cosmic structures. The density of matter in the early universe would have to be far higher than what was previously assumed. Another possible explanation is that these galaxies formed in a manner completely unknown to us. These discoveries are raising questions that demand a reevaluation of the Big Bang theory. Many space specialists are frustrated with these findings, and their voices are often heard in scientific publications. Those who question current theories are often labeled as unorthodox or extreme. Nonetheless, it is clear that even experts who continue to defend the Big Bang theory are confronted with unanswered questions. These questions include fundamental concerns about how, 13.8 billion years ago, something could emerge from nothing. Could something truly emerge from nothing? Or was there a trigger for this event? Or was it just a random occurrence? Stephen Hawking famously pointed out that the nature of time, as we currently understand it, began with the Big Bang. Thus, this process couldn't have been initiated by something else or caused by an external trigger. Similar doubts are raised about the uniformity of radiation and matter across the universe. No matter where we look or at what distance, we observe a similar distribution of systems, nebulae, and radiation across the cosmos. Modern scholars explain this phenomenon through the theory of cosmic inflation, although other specialists have extended this idea, proposing that the universe has expanded in a turbulent manner. According to this theory, expansion occurred only in localized regions like bubbles, while other areas continue to expand indefinitely. This model raises the intriguing possibility that other universes could exist within these expanding bubbles, each governed by its own set of physical laws. This viewpoint suggests that our universe might not represent the whole of existence, but rather be just one part of a much larger and more complex structure. Within this framework, the concept of an eternal cycle of breakdown and rebirth for the universe is advanced. However, this is far from the only perspective in cosmology. In 1955, for example, an article was published in NASA's Big Time magazine, suggesting that the universe may have never had a Big Bang and that it has always existed, possibly for an infinite period. In this interpretation, the expansion of the universe would be non-existent, with the ongoing evolution of matter giving the impression of gradual development over time. One of the more intriguing hypotheses emerges from the realm of quantum physics and string theory. Some tests have suggested that our universe and everything within it could be a projection or simulation from a higher dimensional reality. While this may sound like a plot from a science fiction movie, it has connections to the Kardashev scale, which measures a civilization's level of energy usage based on its ability to harness the power of an entire galaxy. If a Type 3 civilization existed, capable of utilizing all the energy of a galaxy, it might have created an ideal simulation of a universe. However, confirming the validity of such a scenario presents a significant challenge. Exploring the depths of cosmology and the origins of the universe leads us into an area of great mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of existence, testing established theories, and encouraging scientists to reconsider fundamental aspects of our understanding of the cosmos. Central to this debate is the theory of the universe's origin, which serves as the foundation of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from a dense and hot state, expanding rapidly and giving rise to the spacetime and matter we observe today. This colossal event wasn't just an explosion in pre-existing space, it also marked the origin of space itself. The concept of a singularity, where gravitational forces are so intense that the curvature of spacetime becomes infinite, helps support our understanding of this early stage of the universe. However, the discovery of mature, massive galaxies within a few 100 million years of the Big Bang challenges conventional ideas about the speed at which the first structures formed. These findings suggest that the early universe had a much greater density of matter than previously estimated. This raises the question of how such large structures could have evolved so quickly, forcing cosmologists to reconsider how galaxies, such as those observed by the James Webb Telescope, formed so early in the universe's history. One key question stemming from these discoveries is the theory of cosmic inflation, which suggests that the universe expanded exponentially in the first moments after the Big Bang. This rapid inflation is thought to explain the uniformity of the cosmic microwave background radiation that we see across the universe today. However, recent findings are introducing complications into our understanding of the early universe's evolution, suggesting that we may need to adjust our inflationary models. The formation of these early, massive galaxies raises critical questions about the role of dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy. Though dark matter is thought to provide the gravitational framework needed for galaxies to form, scientists still lack a clear understanding of its distribution and properties in the early universe. In response to these unresolved mysteries, theoretical physicists are considering alternative cosmological models that challenge the standard Big Bang theory. Some of these theories suggest that our universe might simply be one of many in a vast multiverse, each governed by distinct physical laws and constants. Such ideas, arising from string theory and quantum cosmology, present a more intricate and interconnected cosmos than previously imagined. One theory gaining traction is that of timeless inflation, in which universes are continually formed within a larger, expanding space. This suggests that our universe could be one bubble among an infinite number of others, each with its own physical properties. The challenge, however, lies in finding observational evidence to support these speculative ideas, as they push the boundaries of what can be tested scientifically. Another provocative theory suggests that our universe may exist within a computer-generated simulation, drawing parallels to the advances in artificial intelligence and computational science, where simulations can recreate complex systems. If true, this concept would fundamentally alter our perception of reality and raise significant philosophical and scientific questions about the nature of existence itself. As observational astronomy continues to evolve, instruments like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, promise to uncover even more of the universe's secrets. Future observations may provide deeper insights into the earliest moments of the cosmos, potentially offering clues about its ultimate fate and the fundamental principles that govern its ongoing evolution. Meanwhile, particle physicists remain committed to understanding the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. In the realm of quantum mechanics, debates about the nature of time persist, with some theories suggesting that time itself might be evolving or even subtler at the most fundamental levels. Understanding the nature of time within the context of cosmology could revolutionize our understanding of the universe's origins and development. Furthermore, the search for extraterrestrial life continues to inspire both public curiosity and scientific investigation. Discovering exoplanets, planets orbiting stars beyond our solar system, has broadened our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope's analysis of exoplanet atmospheres, could reveal biosignatures that point to life beyond Earth. As scientific exploration pushes forward, so too do philosophical inquiries about humanity's place in the universe. The search for answers to questions about existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration will continue to drive discussions across scientific and philosophical disciplines.